Okay, so let's continue with this discussion for this chapter. Basically, we need to talk about a few things. First of all, into how to measurements are happening for length and time, and then we get into the Doppler effect. Hold on. So basically, one of the things that we really need to be examining in here is this parameter gamma. Again, please do not confuse the gamma that you guys have had a long time ago when we were doing physics, when we were doing thermodynamics, namely the ratio of Cp over Cv. So I really want to make sure that that distinction is there. This is just a parameter, a scaling parameter, basically from one reference frame to the other. That's all. So gamma, basically the one that we found right now, is equal to 1 over the square root of 1 minus basically v squared over c squared, or beta squared, as I define beta to be the ratio of these two velocities. A lot of references, they use the velocity u between the two reference plane. That's really not that big of a deal. So we can use the letter u instead, in that the one reference frame is moving with respect to another with a constant velocity, namely u. Okay, if the letter u would fit the bill, and I think it's probably better to use the letter u from now on, is because at some point we're going to be talking, at least in this part, about the acceleration and so on and so forth. So, and typically when we talk about velocity, is the velocity of the object itself, v. Okay, so in this notation is basically beta itself is just u over c. Okay, so that's really what you need to know in here as far as this velocity is concerned. So the parameter gamma itself is of interest in here because we need to know its value. So gamma again is 1 over square root of 1 minus beta squared, and if I plot this function as a function of beta, beta again, just another reminder, is just u over c. Beta cannot be more than 1, so it's at most equal to 1. So it varies between 0 and 1. Okay, and it's equal to 1 exactly. If it is equal to 1, that's for light itself, and that's an exception. Not for a real object, it could be 1. So for a real object, it's always less than 1. Okay, because if it's greater than 1, first of all, this number is imaginary. Doesn't make sense. You cannot scale a length, for example, with an imaginary number. Or if it's equal to 1 for a particle that has mass, then we're going to have a problem, because this gamma, the scaling factor, will blow up to infinity. So this is how the function look like. So this is beta. This is gamma. The maximum value I'm allowing in here is 1 for beta. Okay, and if gamma is if beta is equal to 0, I have the value gamma is equal to 1 over 1, which is 1. And then it's going to start to change, and it's interesting to plot this thing on a function plotter until it blows up to infinity when beta approaches 1 from this side. Okay, then the ratio gamma can go to infinity. Therefore, gamma from this thing in here, it's always greater than or equal to 1. Gamma is actually equal to 1 for non-relativistic speeds, meaning if beta is very, very close from 0, very small, then you can neglect it in front of 1, and gamma will become 1. So that's why we didn't see it when we were doing basically the transformations that are known for Galileo's transformations, because then the transformation would work fine then in this case. So let me rewrite this transformations. Now remember, I just changed the notations. So x prime in the prime coordinate system is equal to gamma x minus u t. Okay, and as far as t prime is equal to gamma times t minus u times x over c squared. Okay, so that's something that you need to be aware of. So if gamma is 1, basically at that point, if c is infinite, if this ratio is 0, that's why t was equal to t prime. So in classical mechanics, this will go to 0 and this will go to 1, and t prime and t are the same for both observers. And this one also, gamma is 1, there is no c in here, so x prime is simply equal to x minus u, and that's exactly how we arrived at 56 miles per hour for a jogger jogging at 6 miles per train on a train where the train is moving with 50 miles per hour. That's the classical mechanics of it. So we recover that stuff from these things, okay? Now, as I said before, I have an object in one frame and I want to measure its length in another frame. So this is the idea behind it. Let's assume that I have an object of a given length L and I want to measure its length, okay? The way normally we measure length is by basically doing the following, and that is you in one frame, it doesn't matter what that frame is at this point, you measure its one side coordinates, let's call this one x1, and it's the other side coordinates, let's call x2, and the length will be so from some origin at some point, okay? And the length will be simply the difference between these two coordinates, x1 and x2, the two ends of the object. Well, it has to happen in the same instant, those two measurements for the two sides of the object, because if the object is moving, or if the frame itself is moving, then we have a problem, because if you wait later and you measure now one end, the other end would have moved and you will get the wrong answer. So the critical condition is that the two times where you make this measurements for this end and that end have to happen in the same time, in the same instant. With that in mind, I want to understand how another person moving with velocity u with respect to this frame would see this length in the new basically with Lorentz transformations. So let's do that. Let's do that quickly. So we know that x1 will transform to x1 prime given by gamma times x1 minus ut1, and then x2 prime will be simply equal to gamma times x2 minus ut2. That's basically how we end up with this expression. Now, if I take the difference of these two quantities to find the measurement of the length in the prime reference frame, L prime now, which is simply x2 prime minus x1 prime, the difference between the two ends is going to be simply, which is actually, let's define it, x2 prime minus x1 prime, is equal to gamma times x2 minus x1, that's L. And then these two quantities are the same because the measurements for the time in here has a condition in order to measure length has to be in the same time. So the length L prime is equal to gamma L. I just argued that gamma cannot be less than 1, always greater than 1. And from the vantage point, from my vantage point, the length now L is equal to L prime as measured in the prime coordinate divided by gamma. So I'm dividing L prime by a smaller number, so this is the length contraction. So length appears smaller. So objects, as they are moving faster and faster, closer to the speed of light, their length appears to be smaller and smaller. In the same token, I'm going to do the same thing with another experiment, and that is requiring that I do an experiment in the same place and record an event at two different instants, a lapse of time. Let's call it, for example, delta t. So my delta t now is happening at two different instances in the same location between t2 and t1. So I'm doing measurement like the tick and the tock of the clock. The clock goes tick tock, tick tock. So I'm gonna record the tick and wait for a later time and record the tock. Clock doesn't move. If it moves, then I have a problem. So again, we have to consider this scenario. So this is the time measurement and the frame in there. So I'm interested to know how that is referred to in the other frame. So in the moving frame, so again I'm going to do t2 prime. I'm going to use the second relationship in here that involves time. Where is it? This one. So I'm going to use this expression in here. So I know t2 prime is related to t1 via this expression, t gamma times t2 minus again u of x2 over c squared. And again I'm going to say t1 prime is equal to gamma times, that's the tock, this is the tick, is equal to t1 minus u x1 over c squared. Well, since this is happening in the same location, those two quantities are the same. So when I take the difference to find the delta t prime is going to be equal to gamma times delta t. Similar to the length contraction, this is actually the essence of the time dilation. This is the time dilations, and objects that are in motion actually appear to be their clocks appear to be running slower, and this is that led to the paradox for the twin paradox, namely that if you have two twins, one of them travels with almost the speed of light, the other one stays in here. The one who stays will experience time dilation. Okay, it's interesting how to resolve this thing in here, because from the vantage point of the twin who traveled, it's actually the other twin who stayed in is the one who's traveling backward with the velocity that is equal to the negative of the velocity of the traveling twin. But for him, then he would say, oh, wait a minute, it's my twin who stayed on Earth who's supposed to age less, and I'm supposed to age more. But there is a resolution to this problem because of the fact that one of them actually had to accelerate. So at some point, one of them was in a non-inertial frame. Therefore, that's how you resolve some of this resolution, some of this apparent, basically, paradoxes. Okay. Please review the lab for more details on these issues. Okay. So here is an interesting problem now, and that is namely the. First of all, let me get into the velocities, and then we'll get into that problem. So let's go back into the expression for x, for the transformations, and we're going to vary it very quickly. So that's why I started with the d's. Oh man, I'm sorry, I didn't mean to do that. X minus, again, I'm sorry, I'm supposed to be using u now, ut, and then t prime again is equal to gamma x prime. Sorry, what am I doing now? My brain is drifting somewhere else. Sorry. U over x c squared times x. Okay, good. I'm glad that I got through this thing in here. Okay, well, what I'm saying in here is that I'm going to wait an infinitesimal change in time where both time and space change. So in this case, I'm interested in the changes, the finite changes, similar to the first two arguments, except now I'm allowing for time and space to change in the same time. And like what I did earlier, which is to do measurements in the same time for both spaces, and do a measurement for in another scenario, the time is at the same location. Now I'm allowing for both of them to change. So what's going to happen now? But infinitesimal. So first of all, the change in position is going to be expressed in a differential form. Gamma times dx minus u dt. And then I have in here in the denominator, in the other expression, dt prime is equal to gamma again times what is it, dt minus u over c squared times dx. What I'm going to do in here, I'm going to find the velocity as measured in the imprimed frame versus that measured in the primed frame. So dx over dt prime, the ratio of these two expressions, 1 over the other. Gamma and gamma cancel. Okay, that's good. So what we're left with is this fraction to deal with, namely dx minus u dt over dt minus u over c squared dx. Okay, I'm going to divide everywhere in here by dt. Technically, we're not supposed to divide by dt because that's actually a symbolic operation. So we're supposed to do this at the deltas and take the limit at the end when the deltas goes to 0, and that's when we can divide. But at this point, we're going to just go to the straight toward the end. So I'm going to multiply by 1 over dt both the numerator and the denominator of this this fraction. So at the end, this is basically what I call v prime. This is the ratio. This is the rate of the change in position with respect to time in the primed reference frame. I will have dx over dt, which is v. That's why I switched actually to this notation now quickly. U dt over dt, that's going to be u, over dt over dt, that's going to be 1, minus u times dx over dt, that's actually v, divided by c squared. Okay, so I hope that you guys picked up the fact that I'm using v for dx over dt, and I'm using v prime as dx prime over dt prime. Okay, quickly now, then if I multiply the last equation in here by c, if you like, or leave it the way it is, that's fine. So let's worry about something in here very quickly. Let's say, for example, v is actually the speed of light. To go back to the experiment where we said, okay, we have a flashlight sitting on, for example, a train, and I'm firing the flashlight, and I want to know how much the light is supposed to go. And the measurements say that V prime is going to be C also if V is C. So let's see if this checks that. So if V is equal to C, so this expression will become simply equal to C minus U divided by 1 minus, remember, V is C, so it's going to be U times C over C squared, which is U over C. Okay, well, this is, just take the 1 over C as a common denominator. So if I multiply both the numerator and the denominator by C, I will have C in the numerator, and then the numerator, I'm not going to change this, I'm going to leave it the way it is. But the numerator, I will have C times 1, which is C. So I multiply the numerator and the denominator by C over C, by the way. Okay, so I multiply the entire expression by the same thing, which is 1. Divided by minus U over C times C, that's U. If I cancel this 2, granting that the train cannot be moving at the speed of light, otherwise this will be a nonsense, then in this case, V prime also is equal to C. So if V is equal to C and sub into this expression, I find also V prime is C. That's why the experiments were not picking up any kind of difference in velocity, no matter how fast trains or objects or airplanes or anything like that moving, and you're shining the light. So the speed of light is the same for all observers, which is really one of the things that we wanted to know. So this is how you transform velocities from one frame to the other. This is if you're moving in this direction. From the vantage point of the other observer, if you do the analysis, V is going to be V prime plus U divided by 1 plus U V prime over C squared. You have to basically be mindful of which way the things are moving. You can argue this, or you can show it is easy to do. Okay, so that's how velocities add. Now let's get into the Doppler effect, which is a very important concept in here. And I know we did that in physics. I don't remember physics 1 or physics 2. I think both of them. We did it probably in optics also, and we did it actually when we do waves. So here is the idea behind it. Okay, in classical mechanics it's easy enough because the source cannot. So basically what you have a source moving with a velocity u. Okay, and we have an observer in here. For the sake of argument, we're asking that the observer stays still, because technically even the observer can be moving with the velocity of the observer. So we're going to keep the observer still. So the velocity of the observer is 0 for right now. Think of this one as being, for example, sitting on Earth, and you have a galaxy moving super fast, that its velocity u is of a relativistic order. Then in this case, this will happen, that the classical mechanics to give us a Doppler effect will need to be corrected. That's why we're doing it in here. So here is the case. The source sends a wave, and this wave will travel a whole distance and reach the observer. Okay? That's the first wave front. So this is the wave front. Front 1. Okay? Then waits a whole period, which I'm going to argue that it's T naught. Let's say, for example, the period of the oscillations that produces this light is T naught, which is related to the internal frequency, which is F naught. Okay, so this is some megahertz somewhere in there, or gigahertz, depending on the frequency of this light. Okay, so we have that, and of course lambda naught. Remember from the dispersion law that is actually obeyed by the previous equation that I mentioned earlier, that's from physics 2, basically that the dispersion law, omega equal to kV, or we write it as C equals to lambda, in this case lambda naught, times the frequency, which is in this case F naught. So this dispersion law works beautifully, and we know it, and we can work with it. Now, this guy though, the observer, sees a wavefront arriving first. Okay, and then a later time another wavefront will come in, because this one is sending them at regular frequencies, at regular times, T naught. For him, for this observer, this wavefront is here, and this wavefront now will move away, and the next wavefront too will reach him. Okay, by the time this one reaches, the first one reaches, the second one is probably here. Okay, this is wavefront 2. This is just emitted from the source. So the source must have moved this whole distance and send it. Now it's on its own. It's going to travel to the observer. Obviously, the first wavefront must have traveled the distance, because now this person perceives the first wavefront and later on the second wavefront and tells the time delay between them is t. There is a time difference between the lapse of time between the two fronts, which is t. So the first wavefront must have traveled, if I go back into when the second one was just come in. So this is the time difference, this is the spatial difference between them, actually, the wavelength lambda. So if he measures the time t, so the second one must have been sent from this point, okay, in space, where the source must have traveled ut, okay? But the first wavefront traveled ct. That's the entire distance that must have traveled. So for him, for that observer, he sees that this wave has a wavelength which is just the distance between the two wavefronts, which is just c minus u times t. That is how much that person will tell that this is the wavefront that person measures. However, this t is not really the t that is t naught. It's because that's his measurement. But the t naught in here is the time in this moving frame at the velocity u. So t and t naught must be related through this relationship. T must be equal to gamma t naught. Having said that, then this wavelength must be equal to c minus u times gamma times t naught. Okay. Well, he still thinks that this is light, and he still sees a specific color for that light, and he still applies for it this dispersion law, with the exception that now he's got a lambda that is not necessarily the same lambda naught that originated from it, but a shifted value, so that his measurement for lambda is different, and so is the frequency. So this expression now, then for him, is that this lambda is from this expression, from the dispersion law, is equal to c over f. Okay, so this is c over f. Okay, and this t naught, which is equal to 1 over f naught, is related to lambda also through that expression. So this t naught, which is 1 over f naught, so this whole thing then can be written as gamma times c minus u times f naught, t naught, which is 1 over the f naught that you're supposed to measure. If I work this expression backward and try to do this one, I can find the perceived frequency versus the actual frequency that the signal has originated from. So flip this expression, flip that one, and divide by c. So this is how we're going to have the frequency in here is going to be hold on, it's going to have an f naught in here, okay, and it's going to have 1 over c, this c, times, yeah, it's going to be in the denominator, and this one, everything becomes in the numerator. So gamma times c, did I put it correctly or not? Times c minus u. I'm sorry. So this, oh man, I cannot do algebra quickly in here. So let's do it there, step by step. Easy. Easy, 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 easy. Easy does it. Okay. Let's first of all divide by c everywhere. So this expression says that 1 over f is equal to gamma times c minus u over c times f 1 over f naught. I'm sorry, because this dimensions has to be exactly non-dimensional, because this is in 1 over hertz and this is 1 over hertz, this is in second, that's in second, so this thing must be dimensionless, and gamma is dimensionless, so this thing also must be speed over speed, which is fine right now, so we're good. So now we can flip things if you want to. So we have f equals to 1 over gamma times this number in here, which is just 1 minus u over c times f naught. Okay, it's just a matter of rewriting gamma, that's all, because this is beta, by the way. This is exactly beta. So this expression then, f equals to square root of 1 minus beta squared divided by 1 minus beta times f naught. the reason why I have 1 over gamma is because gamma itself is 1 over 1 minus square root 1 over the square root of 1 minus beta squared. So when you flip it, it's just going to go to the numerator. So that's basically the expression we ended up with. A trick of algebra in here. This is the square root of first of all, 1 minus beta squared is just 1 minus beta times 1 plus beta divided by 1 minus beta. When I put it in the square root, I better square it. I put this entire square root everywhere times f naught. This and that cancel. So I'm left with basically the expression that I'm supposed to find. This is f naught, by the way, the frequency in the proper frequency, if you wish. So now the frequency is going to be square root of 1 plus, I'm going to restore stuff now, over 1 minus u over c divided by f naught. It's clearly shifted toward higher frequency if u is positive. In other words, if the object is approaching, the source is approaching the observer, because the numerator is more than 1 and the denominator is less than 1, and when you divide by less than 1, you actually end up with a higher frequency. Okay? As a matter of fact, we should be able to retrieve the classical Doppler effect, namely we get rid of everything in here and it should be just the normal one with a denominator 1 minus 1 over c, with the exception that even that you really have to use approximations in there for light, because the speed of objects in classical mechanics are so small. So basically the square root of 1 plus epsilon, if we use the Taylor series, is just 1 plus epsilon over 2. Okay, and that will give me 1 plus epsilon over 2, and the denominator will be 1 minus epsilon over 2, and we basically bring everything. So if we were doing it in so this expression now in classical mechanics, basically in the case 1, beta is very, very small compared to 1. Okay, so or u is very, very small compared to c. So it's going to be 1 plus u over 2c over 1 minus u over 2c times f naught. And if I bring this in the denominator, I will end up, basically what I'm going to say in here is 1 plus epsilon, which is this quantity now, is roughly equal to 1 over 1 minus epsilon, because if I do the Taylor series of this expression and leave just the two leading terms, I end up with this expression. So it's going to be exactly equal to 1 over minus epsilon u over 2 over c minus u over 2c. So it's going to end up with basically 1 over 2ec. So if I do the Taylor series one way or the other, so it's going to end up with either being f naught over 1 minus u over c, or if you wish, it's going to be 1 plus u over c times f naught. In either case, that's basically the expression that we will end up with. And this is identical to what we do when we're doing classical mechanics, fixing the observer not moving and requiring that the source moves with a velocity vu. The other thing in here is that when we're doing astronomy, for example, this expression becomes more important in a sense. We have a better measurement in here for the shift in the frequency, and this will be significant. So for discussing faraway galaxies that are on the edge of the universe, the speeds are so high that we will probably need to use relativistic corrections. So that's going to be important. Okay. Anyway, so the shift actually, which is useful for doing measurements, at least for galaxies and stuff like that in astronomy. So if I consider f minus f naught, all I have to do is just multiply this term by 1 and move it to the other side. So that's going to be the change in frequency is going to be equal to, roughly of course, equal to u over c times f naught. So if I'm interested in the relative shift, namely how far is shifted from the frequency in here, obviously this value can be positive or negative. So in other words, the frequency can be shifted toward higher frequencies. In this case, the object is actually coming towards us, like in this scenario, or it can be shifted toward lower frequencies. In other words, u will be negative. In other words, the object is receding from us. Just by seeing, for example, specific spectral points on the spectrum and seeing if it's in the right place or it has moved one way or the other, then we can tell if the object is coming towards us or moving away from us, and we can tell with what speed too. So this Doppler effect is great, I mean, in trying to find and that's how we discovered that the universe is actually expanding, is just by doing this study. Anyway, so this is the Doppler effect. You have quite a few problems on it too. Now, don't forget that this is the accurate expression for it. Okay, so what we learned in classical mechanics is really first order approximation. For sound it works fine because there was no problem, but for light this is the correct value for the frequency shift. Okay, the one that I reworked now here is just an approximation. It works beautifully for most times because speeds are not that high too. I mean, galaxies don't move with the speed of light, but although they move super fast. Okay, anyway, that's another points in here. And how far we are in here? Oh man, we're half an hour. Let's make a quick analysis for another thing, namely the dynamics. And we have to really be very careful with what we're talking about, the dynamics in here, namely F equals to ma. Before I define F equals to ma, I'm going to define the momentum. Normally this kind of relativity requires a 4-vector, and working with the space-time, basically a continuum and all of that, but we're making it a little bit simpler. Usually this entire course is actually this chapter is a course by itself, so this is just an introduction to relativity. So I'm going to define the momentum as we did define it before, which is mass times velocity, with the exception I'm going to introduce the scaling factor gamma, in this case mv. Okay, so this is the momentum of a particle, and this is what we use for it. So don't forget that this is a particle now in motion, and this particle is moving super fast. That gamma itself is depending on that velocity. Now I'm using the letter v. Okay, so here is the trouble with this expression. If I'm going to do F equals to ma, I'm supposed to say F is equal to, I'm going to use the momentum version of it. I'm going to say F equals to the rate at which the momentum is changing with time. And if I do that, and I take the derivative of this expression, well, the derivative of the velocity with respect to time, that is the acceleration, there is no problem with it. But I have something in here in the denominator that I have to take derivatives with respect to, and that makes matters super complicated. And if I start with a general case, for example, where the velocity has, for example, just two components, x and y component, I will end up with, although the force starts in the x direction, with component of the acceleration that depends on that force and the y direction. And that messes up things big time. Okay, so instead we're going to stick to the one-dimensional case. If it's a proton moving super fast, for example, we're going to stick into 1D, meaning that the Minkowski space, again, x and t, we have the origin of the axis, and this is the moving frame O prime, x prime, and t prime. Okay, nothing about y and z. So this expression now becomes, instead of we're dealing with scalar, with the vectors, we're dealing with the components in the x direction. So P now is mv over square root of 1 minus v squared over c squared, no more vectors. And the acceleration is the rate at which the velocity is changing with time. That's as simple as that in that frame, okay? So if we do that and we want to find the force now and require that the force is given by the rate at which the momentum is changing with time, then I have to do, I'm going to write this one again as gamma mv, okay, as the derivative, first of all, of m is constant, so it's going to be gamma times the derivative of v with respect to time, plus mv times the derivative of gamma with respect to time. You see the additional term that came in, with v only having the value at in the x direction. So we're dealing only with 1d here. Okay? So if we say that, then that's how the force would look like now. There is a term in here. The first term is fine, it's proportional to the acceleration, but what in the world does the second term mean? So this term is the acceleration. So we want to find the second term in here. So plus mv times the rate at which gamma is changing with time, because remember, it's a relativistic particle. It has a velocity super fast, and now somehow it's under a force, electric force or magnetic force or something, so it's going to accelerate further. So if we're doing, for example, the betatron that we did in physics 2, this is the physics that we need to be considering, because the betatron particles start to move super fast, that the relativistic corrections need to be taken into account. And like the cyclotron, where the velocities are not that high, so we could survive with classical mechanics there. Anyway, So we need to find what d gamma over dt is. So what I'm going to do is I'm going to make this expression a little bit simpler for myself. D gamma over dt, namely I want to find the second thing in here. It's the derivative of, first of all, with respect to time, of 1 over square root minus v squared over c squared. Or if you wish, it's the derivative with respect to time of 1 minus v squared over c squared to the negative 1/2. First, from outright, I'm going to drop the negative 1/2 in here. That's what we normally do. So it's going to have the negative 1/2 times the derivative of this expression in here, which is negative 2 times v over c squared times the derivative of v with respect to time, times this expression now lifted to the negative 1 plus 1, which is negative 3 over 2. So it's going to be 1 minus v squared over c squared to the negative 3 over 2. Okay. The negative 2 and then negative 1/2, they cancel. Even the sign is gone. Okay. dv over dt again is a, is the acceleration. That's good because we picked up the acceleration again. So what we have in here is, this is just d gamma over dt, by the way. What we have in here is v over c squared times the acceleration times gamma cubed. Remember, gamma itself has 1 over that stuff there, 1 over, so this expression look like this, 1 over the square root of 1 minus v squared over c squared, the whole thing to the power 3, okay? And this by itself is gamma, so that's really gamma cubed. So this force then has the first component, which is easy to write. So the force then has the first term, which is gamma ma, plus the second term also turned out to be proportional to a, and that's good. Okay, that's the whole reason why we're doing one-dimensional analysis. Otherwise, the acceleration will have all kinds of weird stuff in it too. So it's going to be mv times d gamma over dt, which is this stuff, which is v times a divided by c squared times sorry, I haven't v also to begin with. Remember, I have gamma mv first times d gamma. So I have to write the, I don't know where I got this thing in here from. Let me delete that. So it's mv actually times this stuff times d gamma over dt. So there, let me remind you, it's mv times d gamma over dt. So, and this is d gamma over dt times, of course, gamma cubed. Okay. V times v, v squared. So I have gamma ma, and I have ma times gamma cubed. So I'm going to take a ma and gamma as a common factor in here and everything, and see what we end up with. So this force looks like gamma ma as a common factor, and I'm left with 1 plus, I have a v and a v, that's v squared over c squared, and I'm left with gamma squared in here because I took one of them out. So let's look at this expression in here and see what in the world that looks like. So this whole expression is actually 1 plus, and I use the beta notations, or it doesn't matter, we can leave it as is, okay? I have v squared over c squared times gamma squared, which is 1 minus v squared over c squared. That's it. So the common denominator between 1 and this guy is 1 minus v squared over c squared, 1 minus v squared over c squared, and I have to multiply that in here, so it's going to be 1 minus v squared over c squared plus v squared over c squared. Cancel this and that, so it's only 1 over 1 minus v squared over minus c squared, and that is actually gamma squared. So this whole thing is just nothing but gamma squared. So the entire force then, and that we found is gamma cubed, because remember I have already gamma out, gamma cubed ma. And that's a useful force as long as these conditions are met, that we're dealing with a proton moving only in one direction. So if it's going in a circular path like the Betatron I talked about, you have to be careful in there because that's not going to work. Okay, but in an accelerator, linear accelerator, proton moving super fast, you can apply this expression for it, if in case you decide to accelerate further or something like that. Anyway, so this is the expression for the force. I'm interested in the work, and that will be probably the last thing that we're going to do in this chapter in here. So the work, again, I have again a scenario now. This force that I applied it to a particle that is moving super fast, and now I'm interested in how much work this force will do if the object moves from one location to the other. I hope you guys know where I'm headed with, and that is the work energy theorem, because what I'm going to say in here, if I find the work in here, the work is going to be the change in the kinetic energy. Okay? From there, we're going to find the relationship for the energy, the mass-energy relationship. So, here is the idea. I have a particle that is moving already with a velocity v, and it's under a force F, okay? All of it in 1D, so there is no need for vectors. And then it moved by distance delta x, okay? So I'm asking how much work is done for just this displacement delta w. And that's why I started with the delta w earlier. It's clearly equal to force times displacement. Okay, that's what the work is for this finite displacement delta x. So in this case, then I'm going to write this work as being simply equal to, remember the force I just found it to be gamma cubed ma, gamma cubed ma, and a is just the rate at which the velocity has changed during that time. So it's going to be delta v over delta t times delta x. I'm going to flap things now. We're going to move things in here. Because they are finite values, I can do that. So I'm going to move delta t in here, and it's going to be here and not here anymore. So what is delta x over delta t? That is v again. So basically what the work in here, the finite work that I am finding in here for this small displacement is delta w is equal to gamma cubed mv, because this is v, times delta v. In other words, instead of integrating over space, which is normally what I would have tempted to do to find the work, I'm going to integrate over the velocity, and that's how we actually found the kinetic energy in classical mechanics. That's how we're going to find it now. So, the kinetic energy then, okay, which would be, I'm going to take this proton, for example, started at rest, and now has reached a certain velocity v, and this is given by simply, m is out, m is just a constant, the integral of, again, gamma cubed, that depends on v, so I cannot take it out, and I am left with v dv. Okay, so that's the integration I'm supposed to do now. Okay, let's write this stuff in here correctly. So for one thing, because gamma depends on v over c, and I'm going to make the change of the integration to beta quickly. So I'm going to have m times the integration from 0 to v of v dv over the square root of 1 minus v squared over c squared to the power 3. Or I could have written it 3/2 in here and get rid of that square root symbol. It's the same thing. Okay? 1 minus v squared over c squared to the power 3/2. So, if I divide here by c, and multiply by c squared in here, I'm doing the integration then for beta, and beta is changing from 0 to 1. From 0 to c to beta, I'm sorry, because this is an indefinite integration. So the integration is from 0 to beta, where beta now, please don't confuse this v inside with the v in the integral. This is the basic calculus question, where this is a dummy variable, whereas this one is just a finite value in here. So beta is equal to v over c. Okay, same thing the way I'm defining beta in here. So this is going to be beta d beta over 1 minus beta squared to the power 3/2. And this is equal to mc squared. So this is the change in the kinetic energy. Okay, this is not hard to do actually, because beta d beta, that's d beta squared over 2, and then you move stuff, and then you do the integration. So that's part of the things that you need to finish yourselves. That's one of the questions of the day. Complete this integration. It should be straightforward, okay? The bottom line is the kinetic energy now looks like this. If you do the calculation, it looks like mc squared divided by that factor of the gamma, namely 1 minus v squared over c squared minus mc squared. Okay. So this is the kinetic energy of the object. So it seems like this expression depends on v. If I put v equal to 0, it's exactly mc squared minus mc squared, which is the object is not moving. So if this expression looks like the energy when the object is not in motion, but when the object is in motion, in general, this is its total energy. And that's how we arrive at basically at the expression that the energy now, E, can be written as m prime c squared, where m prime is the mass when the object is moving. It acquires an additional mass in here. Okay. In general, we don't write it this way. We write E equals to mc squared. Okay, where this m is not necessarily, this is m naught actually. This is the mass at rest. Mass at rest. And as the object moves more and more, its mass changes by this factor. Okay, so the expression now is consistent, and this expression, you will need it for your lab, you will need it for a lot of your problems, you will need it for your exam, you will need it everywhere. Not only this expression, all of this, everything in here. I'm gonna stop in here because this video I didn't want it to be too long, but it turns out to be too long. So hopefully you picked up the questions of the day, and you're going to answer them and basically put that in the comments. Thank you.